We will be discussing now binary coded GA. In this particular chapter, we will be going through the introduction. Then we will see how this binary coded GA with an example, some practical case studies that has been solved using BGA. So I have taken just 3 of them. So we'll see the BGA has solved such kind of interesting problems, and then we will close this chapter. So let us begin with an introduction. So as we remember that when we have this multi-variable single objective optimization, we want to minimize the function, and this function is subjected to inequality constraints, equality constraints, and the variable bounds. Now here, as when we understand what is search and optimization, so we are looking for a set of decision variable that will be minimizing or maximizing the objective function, satisfying the constraint. And that is the whole aim which we are trying in this particular course. As of now, we have understood that there could be different problem complexities, such as the problem can have discrete variables, the function can be discontinuous, or there could be some mixed variables such as discrete as well as integer variable or the real variable. The problem can be multimodal. So multimodal means that if I want to maximize this function, so there are 4 points, 1, 2, 3, and 4 points where the objective function is the same and all of them are global optimum solution. Similarly, we can have robust solution, meaning that when we are going to maximize a function, we can get a point on the peak. However, if there is a small change in the value of x, this particular solution will drop, and we can see the function value will drop very sharply. Instead of that, we may be looking for a solution on another peak where a change in the value of x is not going to change much in the function value. And then finally is the reliable solution, where in this particular example, suppose x1 and x2 both are uncertain variable. So under that uncertainty, the solution which you can see as a deterministic optimum solution will become infeasible. So what we are looking for the reliable solution. So under the uncertainty, this particular solution will remain the optimum solution for the given problem. So if we list down the practical properties of the practical optimization problem, it can be non-differentiable function and constraints. We can have discontinuous search space, discrete search space. We can have mixed variable such as discrete continuous permutation. Such kind of variables can be there. The problem can be of a large dimension. The problem can be nonlinear. It can be multimodal. Sometimes we can have more than one objectives, and there could be uncertainty in the variable. The problem which we will be solving can be computationally expensive. For example, when we have this optimization coupled with the finite element analysis or CFD simulation, then the overall optimization task is computationally expensive. And the problem can be multidisciplinary in nature, where we are going to solve a problem that involves multiple discipline. And when we want to optimize such kind of a multidiscipline at a one point of a time, so there also we can use this multidisciplinary optimization. So as of now, except that simulated annealing, all the methods are considered as numerical optimization method. So in those methods, there are certain remarks. For example, one method is not applicable in many optimization problem. So whether it is a case of single variable, or some methods are good for say quadratic problem, but they cannot be applicable for the other problem. And what we do there is we generally approximate the problem and then try to solve it, as we have understood in case of sequential quadratic programming. Constraint handling is sensitive to the penalty parameters. So as you are understanding while solving your assignment number 3, that this constraint handling is actually sensitive to the parameter say R. They are not efficient in handling the discrete variables. And as of now, what we have gone through is all the methods for the continuous variable. There is always a local perspective for searching. For example, if we are going to find the gradient of the function at a point, this means at that particular point, we are trying to find out which direction we should move so that the objective function will reduce. So that is local information we are taking and then moving from one point to another point. Uncertainty in the decision variable and state variables are difficult to implement. If the problems are noisy and dynamic also, the numerical optimization techniques or methods will find difficulty to find an optimal solution. Moreover, when we have more than one objective that we call as a multi-objective optimization problem, numerical optimization technique uh, may not be so efficient for generating the many optimal solution. So looking at all the critical remarks here, our need is to come up with an algorithm which should be innovative and flexible. So answer to this particular question is genetic algorithm. So let us understand what is GA. So first we have to understand that GA is a nature inspired algorithm. So what we see in a nature, so mainly genetic algorithm, it is motivated from the human evolution where we have parents, we have offspring, and generation by generation, we try to improve on it. So these algorithms are nature inspired, but we do not copy exactly the phenomena which is going in the nature. So based on the natural evolution and genetics, we generally create offspring by crossover and mutation. So as you can understand, crossover and mutation are the biological term. So we are not copying them, but we are understanding what is the significance of these two, crossover and mutation, that we will be bringing into genetic algorithm so that the offspring means that the new solution. So when we are creating the new solution, we will be needing crossover and mutation, and there could be more. That is called as natural evolution. Similarly, good solutions are retained and bad solutions are deleted. This aspect is incorporated by following the survival of the fittest. So as we remember, we are going, this is the Darwin's principle and which we are going to use it. And the third is genetics, where we are we are storing an information. So I will discuss all these three one by one. So GA can be used in optimization, learning, as well as in the designing. The important point is GAs are population based algorithm, meaning that instead of one solution, we will be working on many solutions, and uh, uh, these solutions will work together and try to find out the optimal solution for the given problem. So let us understand with the genetics first. So what we mean by genetics. So here you can see two columns, genotype and phenotype. Genotype means what is the information coded in our gene. Phenotype is how we look like. So if we correlate these two terms with ourselves, so we have our gene. So there is a genome inside us, and the genome actually, so that information is coded inside our body. And based on that information, how we look like, our eyes, our height, and the hair color, etc., all of them will be decided by the genome. So genome is inside where the information is coded. Phenotype is how physically the things look. So let us take a cylindrical can 1. So the chromosome we have taken, for example, 10 bits. So if we count, these are the first 5 bits, the another 5 bits. So 5 plus 5, 10. So now as you can see, this is a cylindrical can. So we want to know what is the diameter and height for the cylinder. In this case, let us assume that the first 5 bits represent the diameter, and the rest of the 5 bits represents the height. So in this case, when we are decoding the first 5, we are getting say 8. And when we are decoding the next 5 bits, we get 10. So when we get diameter and height, we can see how is the cylinder. Suppose we are going to change the chromosome. Now you can see that the first 5 bits and the another 5 bits are changed. So when we are going to decode that, diameter and height will change. So currently it is 12 and 14. Now what we can understand is when we are changing the chromosome here, the phenotype will change. And that is what we will be doing in genetic algorithm, that we will be working with a crossover we will be working with a chromosome. We keep on changing in such a way that it will give me some optimal value of say D and H for a given problem. And accordingly, where the phenotype will change and that will become our optimal solution for us. Now let us move to the natural evolution. So in natural evolution means we have to create new solution. So let us take the crossover. So crossover between the two parents. Suppose we are writing P1 and a P2, two binary strings we have taken and randomly at one particular site. So as we can see these vertical lines. So what this crossover says that we are taking this random site and we are swapping the tail. When we are going to swap a tail, you can see we are going to get O1 and O2. So first these strings will be red and after the line blue. Similarly for O2, we have blue color and after the vertical line we have red color. So this concept is, so the crossover as we have understood that it's a biological phenomena. So as and when there is a crossover between two parents, so there is an offspring and the offspring always have the properties of their parents. And the similar phenomena we have simulated in terms of by using this random site and swapping the tail only. So as we can see from P1 and P2, by swapping the tail from the vertical line, we are going to get two different solutions. How these are different? So when we are swapping, either the diameter or the height will change, right? Fine. So once it is done, then we have this mutation. So mutation means that we always have traits from our parents, but still there are certain mutation. That's why we do not we are not exactly same as our parents. So the same phenomena has been taken in genetic algorithm in which when we have this binary string, we randomly pick one bit. So suppose randomly we picked 4th bit. So currently it is written 0. So this 0 will be converted into 1 and rest of the bits will remain the same. That is called mutation. So in both the crossover and mutation, what you can understand is these two phenomena are going to change the binary string. And as per our earlier discussion in genetics, if there is a change in a binary string, we know that its phenotype or the solution will change. The important part of the genetic algorithm is it is based on the survival of the fittest. So since we know this is the Darwin's principle, it says that stronger candidate has more chance of survival than weaker candidate in an environment of limited sources like food. So here, when we are saying that it has more chance, we are always saying that a stronger candidate has more probability of a survival. Now, from what we have understood is when we are going to perform the crossover operator. So for example, in survival fittest, we will be selecting good candidates. On these good candidates, when we perform crossover, then we are incorporating the diversity because the offspring will be evolved from the stronger parent. Why stronger? Because these parents have survived the survival of the fittest. Then the chances are more that the offspring will possess good traits of strong parents, which can be further improved by mutation. This is our discussion. So survival of the fittest is actually selecting good solution. And on those good solution, we perform crossover. Then the traits of the parents will be transferred into the offspring. And after that, there will be a mutation. And there is a high probability that mutation can also change the traits into some good characteristics. So as we can understand from this figure that this is the evolution of human. So this is the first, what we can understand that this was the stronger candidate, and after mating and then having crossover and a mutation, stronger offspring were generated. And because of that, there is another generation. So what we can understand that with the help of survival of the fittest, crossover and mutation, there is an improvement in generation by generation. And that's why at the end, this is what we are right now. So that's why we always say that diversity drives the change in the population. So looking at this human evolution, this genetic algorithm is developed, hoping that this is going to solve the complex optimization problem for us. So since we are learning about genetic algorithm, so let us understand that where this genetic algorithm comes. So evolutionary computation technique or evolutionary algorithm is referred as EA. So let us see on the top of the umbrella, we have computational intelligence, and then we have neural network, evolutionary algorithm, and fuzzy logic. So neural network is a part of machine learning where we have a set of data and we predict what can happen in future. Evolutionary algorithms are used for optimization. Fuzzy logics are um, uh, used to represent the uncertain parameters in our system. Looking at evolutionary algorithm, there are various algorithms. So I have just written very few of them. So one of them is called genetic algorithm. And we can understand that when we are working on genetic algorithm or learning it, it's a part of computational intelligence. So let us understand the flow chart of GA. Here we start with the random initial population. Population means it consists of multiple solutions. Then we evaluate the population and assign a fitness. So how do we understand? Say suppose we have 10 solutions. Then we calculated say objective function of all of them. Then how we will know that which one is good, which one is average, which one is bad. So assigning a fitness means suppose in a one particular class we have 10 students and they are appearing in different courses. So we try to find out what is the aggregate score they get it in the all 5 courses, and then we say this particular solution is rank 1, this is rank 5, this is rank 10. So what we are doing is we are trying to find out which is good, which is average, which is bad. So same thing we do when we assign a fitness. So objective function evaluate PT means we are calculating the objective function, and then we are assigning a fitness means we are trying to find out which is better, which is average, which is not good. Once it is done, we are in the decision box. So T is the parameter which is called as generation counter, similar to the number of iteration. Here capital T represents the number of generation. So if T is smaller than capital T, yes, then we do selection. So we will understand what is selection. Then there is a variation. So we can understand this selection is based on the Darwin's principle, selecting good solution. Variation means crossover and mutation because we have to change the solution. Now, as we have understood that crossover and mutation are going to change our solution, so they are stored in Q. Since all the members in Q are new, we have to evaluate the Q and assign the fitness as we have done earlier with the P. P is referred as a parent population. Q is referred as an offspring population. Thereafter, we have a survivor. So suppose we started with a 10 solution, then we perform selection and variation. We are going to get another 10 solution. So currently we have 10 plus 10, 20 solution. So now this J says that we have to select the best 10 solution because we want to keep the number of solution in the population constant. So 10 plus 10 means we have 20 solution. This survivor is going to again use some kind of survival of the fittest and then choosing the best 10 solutions, increase the counter by 1, and then we keep on moving in this particular loop till the termination condition is satisfied. Once it is done, we terminate and report our result. So let us understand the same genetic algorithm in a algorithmic representation. So we are going to represent our solution, that is genetics. Then we have a generation counter T, small t, and the capital T as a maximum allowed generation. There we initialize the population, means inside the parent population, we are randomly generating the points, basically randomly generating the value of x1 and x2 for each solution. Once it is done, we are going to evaluate, means we have to calculate objective function, constraint, and then assign fitness. Now we are in the standard loop of number of generation. We do selection, so that is survival of the fittest. We do variation, which is crossover and mutation. Then we evaluate, because the solution in Q, all of them are new. So we are going to evaluate, means evaluate the objective function, constraint, and assign fitness. So Q will become offspring population. Thereafter, as I discussed earlier, 10 plus 10, 20 solutions. So we have to use some kind of survival of the fittest so that we can choose the best 10 solutions. And then we keep on moving in this particular loop till T is greater than capital T. So the question is, we are learning genetic algorithm. It should give me the advantages over other methods. So first is, suppose we are solving a problem where there is no good method available to find a optimal solution or near optimal solution. Such problems can be multimodal, discontinuous, or nonlinear problems. So there we can use genetic algorithm that will give you sufficiently good solution that can help us to understand the problem as well as the solution. If the problem is noisy, then it's going to be a difficult problem. The third is the implicit defined problem, meaning that we don't have objective function in terms of equation, but we can calculate the objective function by calling some black box. So this black box, we are giving certain input, it is giving some output. So here, since we don't have any objective function, we cannot use the numerical methods which we have undergone through, because we find a gradient of the function which is not available. So what we can, so in this situation, genetic algorithm is good because it doesn't need any kind of gradient information. If it is a discrete variable problem, GA can very well handle such kind of problem. So as you can see, there is a large class of a problem. GAs can be used efficiently to find the optimal solution. The second scenario is when we are looking for multiple solution. So what kind of problem? For example, multimodal problems or multi-objective optimization problem, where we are looking for multiple optimal solution. So GA can give all these solution in a one run, because GA has GA starts with multiple solution, and that is what we call as a population. No presumption with respect to the problem space. Whatever be the problem we are solving, whatever be the range of x1, x2 and the constraint, we don't have to presume anything. We can directly use the problem in genetic algorithm and solve it. Second is there is a low development cost. For example, we develop genetic algorithm and we are now solving a problem from mechanical engineering domain. Tomorrow, I want to use the same algorithm for civil engineering or energy related problem. So in this case, I can directly use, because only I have to just change objective function and constraints and variable bounds, and I don't have to change anything in GA, and it will work and can give us a good solution. Last is parallel implementation is easier for computationally expensive problem. So as we have understood that if optimization is coupled with say finite element simulation or CFD simulation, then the overall optimization task is computationally expensive. In this case, we can perform parallel computing, means every solution can be calculated on different computers parallelly, and then we can take all the solution back. So that is the concept of parallel computing. So in this case, we can reduce the overall time of genetic algorithm. There are certain advantages as we have understood, but there are certain disadvantages as well. First disadvantage is there is no guarantee for finding optimal solution in a finite amount of time. So this disadvantage we understood with the simulated annealing as well. So if we are going to fix the number of function evaluation or the time, we cannot guarantee that we will get the optimum solution. However, there are some asymptotic convergence proofs are available that says that if we run for a longer time, GA can give you the optimal or a near optimal solution. Second is parameter tuning, mostly by trial and error. When we will see the genetic algorithm, you will realize that there are different parameters we have to tune before we have to start GA. So that is another issue. But there are some self remedies are there, self adaptation. So that can be used with GA to overcome such kind of a problem. Third disadvantage is, since genetic algorithm is a population based approach, meaning we have to calculate the objective function and constraint for the multiple points, then it is expensive. Expensive in terms of function evaluation and expensive in terms of time. So in this case, this is going to be a problem for some. This is going to be a major issue for some problems. However, we can always implement parallel computation to reduce the time. So when we learn genetic algorithm, we should know what are the advantages and disadvantages. So accordingly, we should choose where we have to apply GA. So what is the typical behavior of genetic algorithm on one-dimensional fitness? So suppose you have a one-dimensional fitness, means a single variable function is given to us. So in the early phase, what you can understand is the solution are distributed randomly in the range of X. In the mid phase, we have survival of the fittest, crossover, mutation. Then we are generating new solutions, selecting good solution. So you can see the solutions are trying to move towards the peak. So suppose we are maximizing the function. And the last, we can understand that the solution will converge to the peak. And so in this particular peak, we are going to get an optimal solution for the given problem. With this understanding or the introduction on genetic algorithm, let us understand how binary coded GA works. So here the representation. So I will be following the algorithmic representation. So first step in the algorithm representation was that was a representation. So the meaning that we are going to represent our solution using binary string. So the decision variable for optimization problem are using Boolean variable. Boolean variable means 0 and a 1. So using Boolean variable, I can use them as a binary variable. For example, there are certain problems such as in transportation problem. We have to decide whether we have to take this path or not. So we can assign 0 and a 1. 1 means we have to go, 0 means we don't have to go. Similarly, like switch on and off in electrical engineering. Then we have a real variable. So real variable can also be represented using binary string. Discrete and integer variables can also be represented using binary string. Since we have focused on the real variable, so let us see how this binary coded GA will work with the real variable, say xi. Suppose we have a binary string length of L, which is 5 for xi. So xi is one of the variable for us. So the maximum value of a binary string of length 5 is when all the bits are 1. So you can count 1, 2, 3, 4, 5. So it's a 5-bit binary string, as we have decided earlier. When all of them are 1, it is going to be the maximum value of binary string, which is 31. Let us say this is B. If you want to find the minimum value, means all of them should be 0. The decoded value will become 0. So A is 0, B is 31. That is the minimum and the maximum value of a binary string. Suppose the lower bound of the variable xi is 2 and the upper bound is 10. So we are familiar with the bounds now. So how I can find a value of xi? Xi is xi lower plus, in the numerator we have xi upper minus xi lower. In the denominator we have 2 to the power L minus 1. And everything will be multiplied by dvs. What is dvs? Dvs is the decoded value of a binary string. Looking at this particular information, if we try to fit it into the formula, xi is equals to 2, which is lower bound, plus 8. 8 is 10 minus 2, 8 divided by 31. Why 31? It is 2 to the power 5 minus 1. 2 to the power 5 is 32. 32 minus 1 is 31. And the decoded value of a binary string. Let us assume that we have a binary string of 0, 1, 0, 1, 1. We know how to decode this value. So we start from the right hand side corner and move towards the left hand side. So from the right hand side corner, you have 2 to the power 0 into 1, which is the right bit. Then we have 2 to the power 1 into multiply by 1. So this is the second from the right hand side. And similarly, if we write the decoded value, it is coming out to be 11. So just see how we are finding the decoded value. I'm assuming that all of you know how we are going to decode a binary string. Since the decoded value is given to us, xi is equals to 2 plus 8 by 31. So this formula we have already found in the previous slide, multiplied by 11. This gives me the value as 4.8387. Now, if we talk about the precision, because we are using a binary string, so there must be some precision. Precision is, so we are taking this term 8 by 31 means xi upper minus xi lower divided by 2 to the power L minus 1. So this precision is 0.258. What we mean by precision? Suppose I want to find the next value. Next value means the decoded value will become 12. So you do this calculation and you will find that when you will be taking decoded value as a 12, so the next immediate xi value will be 4.8387 plus 0.258. So that is the next value, and meaning that there will be no value in between these two values. So I suggest I have already given you the value of xi here when the decoded value is 11. Now you take decoded value 12, find the value of xi. So between these two immediate neighbor, you cannot find any other value. So that is called precision here. Suppose we are not happy with the precision. We want more precision in our value. So let us assume that we want a precision of 0.01. Then we are going to rewrite this formula xi upper minus xi lower, which is 8 divided by 2 to the power L minus 1 equals to the precision, which is 0.01. When we put the value, find the L, then L will be 9.65, meaning 10. What we can understand is that when we want a more precision, the binary string length will increase. So that we will remember and we will discuss later. Now let us understand the working principle of genetic algorithm with an example here. So this example is the designing of a cylindrical can. The problem statement says that let us consider that the can needs to have a volume of at least 300 milliliter, and the objective of the design is to minimize the cost of the can of the material. So what we can understand, there is a can, cylindrical can. It should have minimum 300 milliliter of volume, and the price should be minimized. So as we have understood earlier, if we want to design a can, we only need two parameters, which is diameter and height. And from the above statement, the objective function is minimizing the cost and the constraint is on the volume. So as we have understood, the cost can be found by finding the surface area of the can. So this is the surface area in terms of the diameter and the height, and it is multiplied by C. C is some factor, cost factor, that is we are multiplying. So we can get a cost of the can. We have just one volume, one constraint, which is on the volume. So it says that at least. So pi d square h by 4 at least means it can be 300 or it can be more than that. So the sign will become greater than and equals to. And the diameter and height should lie between minimum and a maximum value. Let us assume for simplicity, the diameter and height are lying between 0 to 31 and 0 to 31. So as we have understood, we have to represent the solution. So we are taking 5 bits for diameter and 5 bits for a length. So meaning that 5 plus 5, we are going to use a binary string length of a 10 to represent a diameter and a height. So as you can understand in the chromosome, first 5 bits are used for diameter and next 5 bits are used for the height. So if we just decode first 5 bit, we are going to get a diameter as 8. And if we are going to decode the rest of the 5 bits, then we are going to get a height as a 10. So we generate the initial population. Let us assume that we have taken a population size of 6. When we say 6, this means we are going to create 6 solution randomly. What do we mean by randomly? So the fashion 0101 is coming into the binary string that is randomly generated by our computer. So we generated all the binary strings. So 10 for solution 1, again 10 for solution 2, 10 for solution 3, and so on for all 6 solutions. As per our representation, first 5 bits will be used for diameter. If we decode it, get value 8. Next 5 bit for solution 1, we decode it, we will get a height 10. Similarly, let us take a solution number 2. Let us decode the first 5 bit. So diameter is 8. Next 5 bits, so diameter is 11. So that way we are decoding it. So the decoded value of a diameter and height, as you can see, we have given 8, 10, 8, 11, 14, 6, 12, 7, 4, 8, 5, 8. So what you can understand is instead of one solution, we are actually starting with many solutions or points. And since there are many, we are call everything as a population. Thereafter, we have to evaluate the population. As I have said earlier, I'm following the algorithmic representation where we start with the random population and thereafter we have to evaluate the population. So evaluate means we have to find the objective function. So what is the objective function? So let us take solution number 1 having diameter and a height 8 and a 10. The objective function is the cost term. So we are writing everything here. We get say 22.9, which is equivalent to 23. Then we are finding the constraints. So for the same solution, diameter and height 8 and a 10, when we put into the value, it is coming out to be 502.4, meaning it is already greater than 300, means it is feasible. Then what is fitness? So just let us assume that we are taking some kind of penalty function method. Since it is feasible, so the fitness value is the same as the objective function. So capital F of S is equals to 23. So the fitness is the objective function plus penalty. So here I'm not telling you what exactly is the penalty. We will discuss this thing in the next chapter in detail. So you assume that I have some kind of penalty function method here that I'm going to use it here. So this penalty will be used when the solution is infeasible. So here I'm showing you the table. So I'm writing the index 1, 2, 3, 4, 5, 6 because we will remember the solution from their number. Diameter, height we already calculated. We calculated the objective function and we also calculated this representation. So you remember that we write Gj of x greater than equals to 0. So that's why we are writing G minus 300 and this is greater than 0. Now looking at the value, solution 1, 2, 3 and 4 are feasible, but 5 and 6 are infeasible. Yeah, so as our constraint was represented in terms of Gj of x greater than 0. So the last column of the table, you can see G minus 300 is nothing but greater than 0. Now, as we have understood, the solution 5 and 6 are the infeasible solution. So looking at their constraint violation like minus 199.5 minus 143, we will be assigning a penalty. If you look at the figure on the right hand side, suppose these are the cylinders. So first 4 solutions are feasible and you can see 11 plus 30, 9 plus 40. So solution 5 is 8.2, which we have taken as 9, and we have given more penalty of 40 as compared to the solution having fitness 11. It is only because the constraint violation of solution 5 is more than 6. And as I said earlier, we have one penalty function method, which I will be discussing in the next chapter. So assume that that penalty function method is giving me the fitness as 9 plus 40, 11 plus 30. So that is going to be the fitness value of these two infeasible solutions. For the feasible solution, fitness is the same as the objective function. Now we have calculated the objective function. We look for the termination condition. So currently it is the first generation. So we are going to move into the loop of genetic algorithm. Here I have mentioned that there are some other criterion that can be used for termination. For our simplicity, we are taking as number of generation as our termination condition. Now inside the loop, the first operation which we do is called selection. What is the purpose of selection operator? We have to identify good, usually above average solution in the population. We are going to make multiple copies of these solutions. And if there is any bad solution, that we will be removing them. And those multiple copies will take the place in the place of the solution in the population. So on the left side figure, this is what we have the solution before selection. And after performing the selection, the figure is given on the right hand side. Now let us see how we can do it. So there are many operators which can be used for selection. Here we are discussing just one of them. That one operator is called as binary tournament selection. I have chosen this particular operator. Why? Because it has been used in many of these studies and still people are using it because it is quite efficient. So let us understand what is binary tournament selection operator. So the index, so now the 6 solutions I am writing in the table on the top, and the fitness is also given here. So the fitness means the fitness plus penalty. So as we remember, solution 1 to 4 are feasible. 5 and 6 are represented with the objective function plus penalty. So 49 and 41 for solution 5 and 6 are written here. What this binary tournament selection does. So as you can understand from the name, tournament means there is a match between the two teams. If there is a match, there could be 3 outcomes. First is team 1 will be winner over the team 2. Second outcome, team 2 will be winner over team 2 is winning over team 1. That is second output. And the third is there is a tie between team 1 and a team 2. We are going to use the same, but how one particular solution will be winning, it is based on the fitness value, right? And as we remember, we are solving a minimization problem, meaning the solution which is having less fitness value, we will be selected as compared to the other solution. So since genetic algorithm is stochastic in nature, these are called meta-heuristic algorithm. So we do it this binary tournament selection randomly. So what we are going to do is we have 6 solutions. So we have to randomly pick 2 solutions. So suppose we chose 1 and a 4. So again, 1 and 4 are chosen randomly. When we chose, now look at their fitness between 1 and a 4. So I know that solution 1 is the winner. Why? Because it has a better fitness than solution 4. Now 1 and 4 are removed from this table. So I'm left with solution 2, solution 3, 5 and a 6. Now I pick 2 solutions randomly that are 2 and a 6. Looking at their fitness, solution 2 is the winner. Afterwards, we are left with only 2 solutions, that is 3 and a 5. So we take these solutions 3 and a 5 now. Now, looking at the fitness value of a 3 and a 5, we know solution 3 is the winner. Now what we can understand is when we are performing a tournament between the two, we are selecting solution 1, 2 and a 3, means we selected only 3 solutions. Now here, if you look at the name of the tournament selection, it is called binary. Binary means there is always a tournament between the two. But when we are performing just one tournament, we are just selecting 3 solutions. And we remember that the population size is of 6. So what we will do is we will reassemble all the solution as you can see in the table, and let us perform the binary tournament selection one more time. So in this case, let us choose solution 2 and 3 randomly. Solution 2 is the winner based on the fitness. Then let us choose 6 and a 1 randomly. Then random solution 1 will be the winner, and then the left out solution are 5 and a 4, and 4 is the winner. So performing binary tournament selection twice. So in first tournament, we selected 3 solution as 1, 2, 3. In another tournament selection, we selected 2, 1 and a 4. There are certain interesting properties with the tournament selection, as if we look into the table, the best fitness of the solution is 2. If we say that how many times the solution 1 is the winner, so as we can see, 1 is the best solution. In the tournament 1, there is a 1 solution. Solution 1 is the winner. In tournament 2 also there is solution 1. Means solution 1 is the winner in both the tournament. So it is happening. Why? Because solution 1 is the best solution. As and when it will be having a tournament with any of the solution in the population, it will always win. Let us look at the solution number 5, which is worst solution. How is the solution number 5 is the winner in any of the tournament? As we can see, 1, 2, 3, and on the second tournament 2, 1, 4. So 5 is not there. It is because when 5 is playing tournament with any of the solution in the population, it will always lose. So that's why 5 has no copy. For other solution, we cannot say, because other solution can be winner 2 times, 1 times, or it cannot be winning any of the tournament because it is a stochastic operator. So after performing, so graphically, I'm showing you the same binary tournament. 2 solutions, 2, 23 and 30 having a fitness. They are selected randomly, 23 selected, then afterward 24 and then 37. So we have selected 3. Then again, we perform the binary tournament. So we selected 24, 23 and 30. So if I go back, so you remember that in a selection operator, before selection, these are the solution, and after performing the selection, these are the solution which we have selected, and these are selected using binary tournament selection operator. Now, once we have selected the good solutions, now we have to perform crossover on them. So first of all, let us understand what we mean by crossover operator. This crossover operator is responsible for creating new solutions. So basically we are exploring the search space so that we can find where is the optimum. There are different kind of crossover operators such as single point, endpoint, and uniform crossover. We will be focusing on single point crossover in this chapter. So 2 strings are picked randomly in most of the crossover operator. So let us assume the single point crossover operator for the CAN design. So P1, P2 means we have selected 2 solutions randomly from the population. So the red is represented by P1 and blue by binary strings are represented by P2. You remember that how we do crossover. So randomly we draw this vertical line and then we swap the tail. So if we are going to swap, if we swap the tail, C1 and C2 means these are offspring 1 and offspring 2. Offspring 1 means red, and after the vertical line, everything is blue. Similarly for offspring 2, we have blue, and then after vertical line, everything is red. Means we have swapped the tail of P1 and P2 along the vertical line. Just for understanding, you can see that the diameter and height and the fitness are given here. The observation is the C1 has a fitness of 22.4, which is better than the fitness of P1. And you remember that we just performed the binary tournament selection. In that case, we find that the solution having 23 fitness was the best in the population of 6. What we can understand is we perform the crossover. Now we have a one solution which is having a fitness of 22.4, which is even better than the best fitness after the tournament selection, meaning that crossover operator can generate new solution which can be better than the parent solution. Second observation is look at C2. The fitness is 39. Now 39 is not good as 23 as well as 37, meaning that crossover operator can create a better solution as well as sometimes can create bad solution with respect to the parents. Now the question is, should we worry that crossover is when the crossover is generating good or bad solution, because it is totally random, because the vertical line which we have chosen, it is based on the random. This is based on the random point. So the point is, if suppose crossover operator is generating the good solution, then we should not be worried. Why? Because in another generation, this particular solution will be selected twice by the binary tournament selection, and after performing crossover and mutation, it can generate even better solution. But if it is generating bad solution, we should not be worried again. Why? Because this bad solution will be deleted after few generations by the say binary tournament selection operator. So as what we have discussed, that the crossover operator can generate good as well as bad solution with respect to parents. Bad individuals or solutions will die during the reproduction. Reproduction means selection operation in further generation. Good individual will get a multiple copies in next and further generation. As crossover was done on two parent which survived the tournament selection, more likely new solutions and offspring will contain good traits of parents will evolve as a better solution than their parents. So from the previous example, we can understand that there is a large probability that when two good solutions are having the crossover, the new solution will be even better than their parent solutions. Now, as we remember that inside the algorithm, after performing selection and then crossover, now we have to perform the mutation. What is mutation? Mutation operator is also responsible for the search aspect of the GA. Means we are going to change the binary string because that will change the value of a diameter and height. And finally, our fitness will also change. So the need of the mutation is we want to keep the diversity. It is because if we do so much of selection, then all solution will become the same. And then this crossover is not going to help us. So in that case, this mutation will help us to keep us the diversity. So let us take this particular string so that you remember that the fitness of C1 was 22.1. So we have taken the C1. Now C1 string we have taken, and randomly we went to the fourth position, which is currently 1. And now we are mutating this 1 to 0, and rest of the bits will remain the same. Now the second bit is the solution which is generated after mutating C1. Now look at the fitness value. The fitness is further reduced to 16.32. Look at the volume. Both are feasible solution, meaning that this mutation solution can create good solution. It means that the mutation can create a good solution for us. But as similar to the crossover operator, it can generate the bad solution as well. So with the same remark, if it is good solution, it will get multiple copies in the next or further generations. If it is bad solution, it will be deleted by the selection operator in further generation. Here we have to understand that mutation is generally done with a low probability. So we do not do a mutation very drastically. We do it with a very small probability. Probability means that if the random number is smaller than this particular probability, then only we mutate, otherwise we do not. So the example which we have solved right now, let us understand their graphical illustration. So this is, suppose we have one of the problem given which has two constraints and we have a variable bounds. The optima is lying at the red dot and the blue dots are the initial population. So means the solutions are randomly generated along x1, x and a y. Once it is generated, we evaluated it, then we perform the selection. So when we perform the binary tournament selection operator, now you can see there are two blue dots. This means this solution get 2 copy. Another 2 blue dots, this also get 2 copies. This also get 2 copy. The single blue dot will get 1 copy. There are solutions which are not filled with the colors, only the circle, black circle, circle with the black line you can see. So these are the solutions which are not selected by the binary tournament selection operator. As we remember that we do crossover, so we randomly pick two solutions. Suppose two blue dots we have taken and perform the crossover. So that resulted in the brown solution. So these are the crossover solutions. Now, as you can see, these are the brown dots and there are purple color dots as well. So brown dots are the solutions which we get after crossover. And then we perform the mutation. So we get these purple or you can say pink dots. So these pink dots means there are small perturbation for some of the solutions because we perform mutation with a less probability. Now at the end, what you can see that the figure on the right hand side, this is the initial population. And after one generation, you can see these blue dots are moving towards the red dot, which is the optimum solution. So since these solutions are moving towards the red dot in some way, so we can expect after few generation, these blue dots will converge to the optimum solution. And that is why GA will get the optimum solution for the given problem. So with this understanding on genetic algorithm, let us have the case study. So I will be discussing 3 practical case studies that are very interesting. So first is the tracking suspect. This study was done in 1991 by these two authors. So the point was that if you see a suspect, then if you have to tell the detail, then you have to recall the suspect. OK, he was there and his forehead, his chin, his eyes color, height, etc. You have to remember. Then there is one person who is artistic. Based on your explanation, he will be writing it. You might have seen in many of the movies that somebody is explaining how was the suspect and somebody was drawing and giving the drawing of the suspect. Now the point is, if you have looked the suspect for the first time and just for a short duration, you may not recall each and everything. So therefore, what these two scientists did, they took forehead, eyes, nose, mouth and chin as their variable. And for every variable, they are taking 7 bits. So 1, 2, 3, 4, 5 variables are there. So 5 into 7, 35 chromosome string they have taken. Now, thereafter, they are using a one fitness. How they are calculating the fitness. So 1 to 9 scale. 1 means it is very bad. 9 means it is the picture which it will be shown has it is matching with the suspect. So what is happening is that the eyewitness who has just seen the suspect, they are given a computer screen, and then they have a database of forehead, eyes, nose, mouth and a chin. So they keep on changing those values. By looking at the picture, every picture you are giving a fitness 1, 2, 5. So this means that when you are giving the higher fitness means the picture is resembling more to the suspect. And in that case, so that is the way they started it. So for their sample, they took a population size of 20. They used one of the selection operator called SUS. And this we have not discussed, but you can assume there is one selection operator called SUS. 1 point crossover is used and bitwise mutation was used. So both of them we have discussed. So you will be surprised that this was the original picture of the suspect. And by showing different combination of the forehead, mouth, nose, eyes, the eyewitness was looking and giving the fitness, and then the final design or final picture of the suspect was given here. Now, as you can see, both of them are not exactly the same. Like for example, you look at the eyes, nose and the mouth, but I am pretty much sure that if this simulated picture is pasted, then anyone can recognize the suspect if he is there, and the person can inform the police. What is the interesting part here is application wise, it is very interesting application. And look at the optimization wise, we don't have any objective function written in the terms of x1, x2, x3. So we don't have any mathematical form. So I cannot use any of the numerical optimization technique to solve this problem. Since GA doesn't need such kind of a thing, we are able to solve it. And you can appreciate that in 1991 itself, this study was done and they were quite successful in solving this particular problem. The another case study is the antenna design problem, which is another interesting problem. The objective function is we want to minimize the difference between the average gain and then antenna gain. So that is what is their objective function. So they are going to determine X, Y, Z coordinate of the 7 wire. So these 7 wires are their ends are connected to each other, and the first wire starts from the origin. So this means that only the first position is fixed and rest of the corners of the wires that are variable. So X and Y, Z coordinate we have to identify, and these wires are connected to each other. The antenna must fit into some kind of a cube, which is 0.5 lambda. So they used 105 bit chromosome for solving this particular problem. So as you can see, X1, Y1, Z1. So they have a plus or a minus sign as well as 0, 0, 1, 0. So this is a binary string for them. Now, what is the interesting part here is they solve the problem using genetic algorithm. They get this particular antenna, which you can see inside the box. What is the interesting point is once they get this design, they filed a patent. So this is a US patent, and this US patent is approved now, is already approved. So the point is, although this design of the antenna may look similar, easier for us, but before that we did not have this solution. Everything is done by GA. Only the problem formulation was given to genetic algorithm. GA solved the problem, gave the best solution for which the optima we don't know. And once this design has come, the authors of this particular antenna design, they filed a patent and they have the patent now. So that motivates us that suppose we are solving some research problems or some problem which is difficult to solve, we don't know the optima. This GA can give you a solution that may be something different solution, and on that solution you can even have your patent or your product on your name. Coming to the third case study, that is the coffee composition, which is another very interesting study using genetic algorithm, or this is solved using one of the algorithm under evolutionary algorithm. So here in the figure on the left hand side, what you can see that these are the coffee jars. In these coffees jar, you have different coffees from different places. For example, from Africa, India, or Sri Lanka, something like that. Now, these pipes are coming here, and then different compositions or combination of these coffees are mixed in the jars. So as you can see, there are multiple jars here. Now, with the help of genetic algorithm, different combinations are put together. So suppose if we say one of the parrot, so it says that 25% of the from Colombia, 40 from Sumatra, Java, Bahia, and Jamaica. So different combination of the coffees are taken, and then they are put in the jar. So this guy, he's also the author of this paper. He is basically tasting the coffee. And while tasting the coffee, he is giving the fitness. Fitness means say 1 is bad, 10 is good. So in that way, he is generating the Office Spring solution, as you can see here, Office Spring 453 using the operators. And finally, this genetic algorithm or other evolutionary algorithm was able to give him the best combination of the coffee that he liked the most. It is very interesting in this study. Again, for this study, we do not have any objective function which is written in terms of variables such as x1, x2, and x3. So with this, I'm concluding this particular chapter on genetic algorithm. So we started with the introduction of an optimization as a recap. Then we talk about the generalized framework. So that algorithm representation and the flow chart we discussed. And according to that, we understand binary coded GA and its principle. So the working principle we have gone through with the example of the CAN. I showed you 3 case studies from the practical, from the practice, and that can motivate us to use genetic algorithm for those problems for which we don't know where is the optima or the problems which are difficult to solve. So with this, I'm concluding the chapter on